It's my great pleasure to introduce Gilbert Bernstein, who will be sharing with us some of his amazing work in high performance languages for visual computing. Gilbert got his PhD from Stanford working with Pat Hanrahan and is now a postdoc at Berkeley and MIT working with Jonathan Reagan Kelly. Gilbert's work lies at the intersection of computer graphics and programming languages and spans a really awesome space of applications from physical simulation, optimization, differentiable programming, hardware design languages, and a lot more exciting things that I am looking forward to hearing about today. His work has been published at Top Graphics and PL Venues and has been incorporated into multiple industry products at Adobe, Autodesk, and Disney. So Gilbert, please take it away.
Thanks so much, Adriana. And thanks everyone for coming. I'm really excited to be here giving the talk. So what if there were an earthquake tomorrow? What if we don't do anything about carbon emissions? And what if I wanted to be Shrek? Computer simulations of both physical and less physical phenomena give us a way to imagine different futures, while optimizations help us work out how to change those futures. For instance, how can we make buildings safer? How might we forestall climate change? And how do I turn this thing off? So simulation and optimization are two of the pillars of what I'll more generally call visual computing throughout this talk. This category involves many other important classes of problem as well. Simulation and optimization of the world around us generates a near inexhaustible demand for more resolution and therefore more computation. For instance, consider a fluid simulation discretized on a grid, or a 3D reconstruction on a grid, or a shape optimization problem on a grid. In order to increase resolution by a factor of 2, 8 times as many cells are required. And for simulations, twice as many time steps are required to maintain the same degree of accuracy. So something as simple as increasing spatial resolution immediately generates asymptotically large demands for resources. Techniques from many disciplines are therefore used to try and tame these asymptotics. For instance, programs are written to use parallel hardware ranging from SIMD to custom accelerators. Numerical analysts design and refine algorithms for linear algebra, optimization, and integration. Different geometric data structures represent data at differing levels of fidelity and complexity, while different physical and mathematical models approximate the phenomena of interest in different ways. Writing a specific program requires combining an appropriate choice of such methods. But when we actually go to write the application, we end up entangling all of these concerns together in the program's source code. And this process repeats for each new program that gets written. If we think about this in terms of people rather than in terms of programs, we might start by trying to build a team of experts, but quickly find ourselves relying on super experts who can wear all of the hats necessary to maintain the system. As the code base grows, we start trying to build teams of such super experts. And this isn't just a nice story I'm telling you either. I was told by a chemist that he has to teach his chemistry students a substantial amount of numerical analysis and high-performance software design before they can start doing simulation-based research in chemistry. This state of affairs is costly because training and recruiting super experts is costly, all of which serves to limit performance in practice, besides having other negative consequences. So for these reasons, achieving a separation of disciplines is essential to progress in high-performance visual and numeric computing. Programming languages, especially domain-specific languages, are some of the most powerful tools that we have to define such interfaces between experts. For instance, in computer graphics, shading languages have been essential to the architecture of both batch and real-time renderers for decades. And newer image processing languages like Halide help accelerate YouTube and Photoshop. If you look at video game engines and CAD tools, scripting languages isolate higher-level programmers from the performance-critical parts of the system. In fact, you can't use the highest performance hardware today without using DSL. So while we think about systems like TensorFlow and PyTorch as automating away the details, that would be to neglect the experts who develop these frameworks, the performance engineers who optimize key subroutines, and the architects who design new accelerator hardware. What the end user experiences as automation is more often than not the result of a better separation between experts. So in the first part of this talk, I'm going to discuss two languages I worked on that take vertical slices through two application domains, simulation and optimization. And then in the second part of the talk, I'm going to dig deeper into some horizontal DSLs focused on addressing concerns that span across many different application domains, such as extending automatic differentiation to handle discontinuous phenomena and maximizing performance at the bottom of the stack. Finally, I'll conclude by talking about some of my ongoing and future work. In terms of tempo, the first part will rapidly establish some basic themes, then we'll slow down for the second part of the talk, and finally pick up the pace again at the end. So first up, let's talk about a language that allows for parallel portability of simulation code. We're going to achieve this portability using data abstraction ideas from databases. But before I get started, as well as periodically throughout the talk, I want to remind everyone that research is a group endeavor and acknowledge the many collaborators I've been lucky to work with. Okay, so consider a simulation program. These tend to be written using large amounts of Fortran code. Whether that's Fortran written in Fortran, C, or Python is another matter, but whichever way, it ends up reducing data structures to arrays, arrays of indices to other arrays, and on and on. Programmers, much less the compiler, have trouble making sense of the code required to access this structure. And as time goes by, the data structure and access patterns become fixed in ways that are difficult to change, because more and more code gets written that encodes the data structure access patterns within it. Which of these loops can be parallelized safely? As long as we're trying to automatically reverse engineer every clever trick that people hard code into their high performance programs, automatic parallelization is destined to remain a pipe dream. Stepping back, this morass of hard-coded access patterns is reminiscent of the situation in databases before the introduction of relational algebra. Relational algebra was popularized via SQL, possibly the most famous domain-specific language. And despite being designed decades ago, SQL hasn't had to change at all to take advantage of new parallel hardware. This latent data parallelism in SQL queries comes from its data model, sets. Sets take the freedom of specifying order of computation away from the application writer to reserve it for the compiler writer. So our idea with the language EB was that we can represent spatial data structures using ideas from databases like relational algebra. And if you aren't familiar with relational algebra or databases, you can just imagine them as spreadsheets. With that in mind, let's see how we can describe high-performance computing using Excel. So recall the dragon simulation. We discretize the shape using a tetrahedral mesh, which is made up of many individual tetrahedra, as well as vertices, edges, and faces. You can think of there being a spreadsheet for each of these different sets of objects. Each row of the spreadsheet is an element of the set, such as a vertex. And each column is a field of data, such as coordinates of vertices. These columns are the arrays that we were talking about earlier, but now connections between different sets of elements are explicitly typed and can be augmented with special data structures for inverting the connections. EB programs then look like imperative looping code over these sets of elements. EB further allows nested loops over neighboring elements, which are implemented using these auxiliary data structures. By modeling data and control flow abstractly, simple program analyses can now determine whether or not a loop is safe to parallelize, rather than trying to reason directly about the generated code. But this raises an important question. Does introducing data abstraction inherently degrade performance? The short answer is no. So FreeFEM, FEM is FEM or finite element method, is an existing high-level language for solving partial differential equations, which we compared to this system at the request of our reviewers. And as you can see, the EB version of this elasticity simulation runs 6,800 times faster. So this kind of performance gulf is in fact representative of real systems like MATLAB, but doesn't really tell us much about EB. By contrast, here's a comparison to a simulation handwritten and optimized by NVIDIA engineers. LULESH is a benchmark from the national labs, which has been implemented in dozens of different programming languages and programming models. Our version in EB is between twice as fast to 20% slower than two different implementations from NVIDIA, each tuned for different generations of GPU architecture. And this shows that you can get state-of-the-art performance with a system like EB despite the data abstraction. Lastly, note that writing code in a DSL usually tends to reduce the amount of code that needs to be maintained. So most libraries don't have carefully hand-tuned GPU implementations. The authors of the Vega Elasticity library tried to add multi-core support to their originally single-core library, but left much of the code serial. You can see here that the benefits of this kind of opportunistic parallelization are limited. By comparison, our re-implementation of this slice of Vega had 4 to 9 times speedups by using the GPU. Now, this isn't an apples to apples comparison, I realize, but the point is that the GPU version of the EB code is already available without us having to write any additional code. This is the kind of practical benefit of achieving a better separation of concerns. So next, I'm going to talk about a language for creating high-performance GPU solvers for a particular sort of optimization problem. We're going to be able to create these solvers from high-level problem descriptions using automatic differentiation. Again, I want to take a second to thank all of my many collaborators on this. So a great number of different problems in computer graphics, image processing, and computer vision can be posed as nonlinear least squares optimization problems. For instance, the intrinsic image technique decomposes a given image into the product of unknown reflectance and shading source images, by which I literally mean the pixel-wise multiplication of these two images. To formulate this as an optimization problem, we first replace the equality with a sum of squares energy, where we're summing over all pixels, and then add in some number of additional energy terms representing regularization or prior assumptions on our unknown quantities. The details here aren't important for us beyond observing that we're computing the sum of a bunch of squared terms, each of which is a local, possibly nonlinear function of our unknown variables. So we can concisely express such energies using a DSL. First, we declare our variables and whether they're known or unknown. Then we can add energies to the problem. We can also do things like form intermediate stencil values, averaging the neighboring pixels, for instance, and use that to express the regularization energy. In general, this allows us to specify arbitrary nonlinear least squares problems. So given a particular nonlinear least squares problem, it's quite a mouthful, we can apply any one of a number of standard numerical algorithms to find a solution. These algorithms require not only the energy function as a subroutine, but also various different kinds of derivatives of the energy. Again, the details and terminology aren't that important for us here. The key points are that we need to compute certain matrices from our energy specification using automatic differentiation, and that multiplying vectors by these matrices is the inner loop computation of the numeric methods that we're applying. So given a problem specification and a choice of numeric algorithm, we need to figure out how to actually implement a solver. Prior to OPT, there were two main approaches: write everything yourself by hand, or try to use an off-the-shelf library. These off-the-shelf libraries work by using automatic differentiation to construct sparse matrices, which are then used by the algorithm. However, rematerializing this problem matrix at the beginning of each outer iteration and repeatedly reading it in the inner iteration leads to order of magnitude overheads in comparison to handwritten solvers. By contrast, handwritten solvers are great for performance. The problem is that handwritten solvers are considerably more complicated to write. And even worse, they mix all of the different problem concerns, including calculus and high-performance computing, together. So OPT eliminates this trade-off by passing code from automatic differentiation to the solver at compile time rather than passing data at runtime. DSL compilation then enables us to generate this highly specialized stencil code, which allows us to preserve the locality structure of the input problem. So opt programs are 4.5 to 11 times shorter than the equivalent hand-coded CUDA solver and far less redundant. For instance, adding an energy term to the CUDA requires consistent updates in at least 3 independent places, which might explain why every handwritten solver that we compared to had at least some performance degrading error in the derivatives or boundary conditions. Compared to existing high-level libraries, opt is also orders of magnitude faster. For interactive applications, this isn't just a question of cycles saved on servers, but a make or break distinction. A real-time application that runs at 1 frame per second simply doesn't work. And even compared to the existing handwritten GPU solvers, opt generates faster code. So opt has seen a modest amount of adoption, being used in a number of other papers, and being used internally at a number of companies. Opt is available as open source software and has been cloned thousands of times. So with opt, we managed to facilitate a higher level separation between applications and high performance optimization solvers. But this came at the cost of requiring the compiler writer to become an optimization expert. This raises an important question in the design of DSLs for visual computing. How can we push more responsibilities away from the compiler and back towards the appropriate groups of experts? And now's a good time if people have some questions on the last 2 parts. I'll pause and take those.
I can jump in quickly if that's all right. I was typing, but not quickly enough.
Oh yeah.
Gilbert, can you maybe give a short answer, if one exists, to the question, why not just optimize MATLAB as people have been trying to do for a couple decades?
So, I mean, if we take specifically opt that I just talked about.
I was thinking more Ebb, but you're welcome to take it in either direction or both.
Sure, yeah. So for Ebb, if you start doing like nonlinear stuff in simulations, it's kind of a pain to write it in MATLAB, which is really optimized for writing linear algebra expressions. So you're going to drop down into like the imperative code version of MATLAB, which is just crazier slow and not compiled well. Where MATLAB seems to do okay is if all of your operations are just going to get targeted down to BLAS operations or LOPAC operations, and those exist in a library and they're reasonably efficient, and you don't need to fuse those, then MATLAB might not give you terrible performance. But like in this opt case, obviously it's not going to assemble a matrix-free iterative linear solver for you.
Great, thanks.
Any other questions? But in one sense, you could, like, it's not a terrible thing. It would be nice if we just had MATLAB and it ran fast for all these things. So like, that's definitely the right vision to have in mind. Cool. Well, I'll go ahead and keep moving on and get some more questions at the end. So to recap, we discussed one simulation DSL that achieves parallel portability using data abstraction ideas from databases, and an optimization DSL that uses automatic differentiation to create high-performance GPU solvers. In each case, we achieved a partial separation of concerns, but either left the application programmer or compiler writer with significant extra responsibilities. Similar issues constrain other DSLs for numeric and visual computing to their own particular vertically integrated application domains. And nonetheless, certain themes have recurred, including the importance of automatic differentiation and the exploitation of hardware acceleration. So in the second part of this talk, I'm going to discuss my more recent work digging into these topics. The first of these, it might seem like automatic differentiation is a perfectly well understood and solved problem. That isn't quite true. Again, I want to acknowledge my collaborators on this project. And if anyone knows Kevin, feel free to get on his case about not giving me a picture. So consider the language opt that I mentioned earlier. One of the most common uses of nonlinear least squares is for solving inverse problems, where we know the forward model and the output, but not which input will produce that desired output. So the nonlinear least squares example that I gave earlier is one such inverse problem, where the forward model is simply multiplication. Machine learning problems expressed in TensorFlow and PyTorch are also frequently posed or could be posed as inverse problems. Simply, they're solved with stochastic gradient descent rather than with nonlinear least squares. The almost unreasonable success of such nonlinear optimizations might lead us to believe that we can just invert functions in practice by taking gradients. Would this mean that we can solve computer vision by just inverting rendering? Or that we can rewind time by inverting simulations? If we want to try out such provocative ideas, we need some way to make renderers and simulators differentiable. One obvious approach would be to grab a textbook renderer and apply textbook automatic differentiation. And even if it doesn't actually solve computer vision, you'd expect at a minimum to get the correct gradients out. Turns out this isn't even true. So the problem comes from the fact that rendering is all about computing integrals, both over pixels and over hemispheres of reflected rays of light. Even more specifically, it's because we're trying to compute integrals of discontinuities, which occur due to naturally discontinuous phenomena like silhouettes of objects or contacts and collisions in simulation. To get at the essence of this problem, I'm going to replace our 2D integral here over the area of a pixel with a 1D integral over the unit interval, where the silhouette of an object has been simplified all the way down to a step function. At the same time, we can interpret this integral probabilistically as the odds of a p-biased coin coming up heads. And one little bit of notation, I'm going to go ahead and use these blue brackets to notate the indicator function. It evaluates to 1 when x is less than p and 0 otherwise. So analytically, we know that this integral is simply p. So taking its derivative with respect to p is simply 1. And in case that didn't sink in, let's look at the example a second time with visuals instead. The indicator function is a step function with a discontinuity at position p. Then observe that as we sweep p from left to right, the area under the curve grows linearly, meaning that the integral is linear as a function of p. Finally, the derivative of the integral is just the slope, which is 1 in the relevant parameter range. So now that we have our example and we understand the analytic behavior of it, let's try to evaluate the same integral using a computer program. This program generates n samples, basically the n coin flips, with each one drawn from the interval between 0 and 1, and increments a counter if x is less than p. But if we automatically differentiate this program, we get a program that never ends up incrementing the counter, and so must always return 0. This happens because automatic differentiation ignores expressions inside of if conditions, meaning the x is less than p expression in the red box here. So if that seems strange, let's go ahead and look at this sampling procedure visually, and maybe the problem will be more obvious. An infinitesimal change to p really doesn't change the value of the function at any of the samples. Or put another way, the derivative of the indicator function is 0 almost everywhere except at p, where it's not properly defined. The deeper problem here is that our program isn't actually equivalent to the integral. Rather, it's a discretization of the integral problem. And we get different results if we choose to discretize these programs before or after differentiating them. So to resolve this problem, we designed a programming language for directly writing integration problems. And while there are plenty of papers addressing the mathematics of this phenomenon by hand, we were the first researchers to propose a systematic way of computing these derivatives on computers. To be explicit, we directly encode these integral expressions into text expressions where these sorts of brackets are the if conditions that were giving us trouble before. These expressions can be much larger with nested branches and integrals as well. So when we take derivatives of expressions, we follow the normal derivative rules until we reach these branches. Naive automatic differentiation simply ignores the branches, whereas our method forms additional Dirac delta terms as well. Because derivatives are linear, we can always rewrite this expression to move deltas up to the integrals. And then we can rewrite those delta expressions and cancel out the integrals against the deltas. And if you're not familiar with Dirac deltas, again, don't worry. The key point here is that they let us compute the correct derivatives of integrals of discontinuous functions, which is a mouthful, but as we just saw, naturally occur anywhere that discontinuities occur, such as in the silhouettes of objects or due to collisions in context and simulation. To demonstrate that getting this right makes a difference, we looked at two toy applications that are representative of how this phenomenon manifests in rendering and physical simulation. The first application we looked at was image stylization via triangulation. In this inverse problem, we're given a fixed triangle mesh with unknown colors and unknown vertex positions and a known rendering function. The goal is to find a triangle mesh that best approximates the image. So when triangles are flat shaded, the naive gradient of the triangle vertices, is 0. Therefore, as shown in the middle here, the triangles never move. By contrast, incorporating the delta terms into our optimization causes the mesh geometry to conform to the edges of the image, as you see on the right. In fact, even when the naive method does provide gradient signal, such as when we switch to linear interpolation for shading, the result is often noticeably worse. Taking these derivatives automatically also saves us a ton of work, as evidenced by our colleague who hand differentiated a quadratic shading model before we did this research. So the second application we looked at was classic trajectory optimizations used in computer animation. The basic idea behind these is that physical trajectories of systems are those that minimize effort, where effort is some function of position and velocity. And the overall effort is the integral of this quantity along a curve. So if we can model discontinuous velocities along our trajectories, and we can model discontinuities in this effort function, then we can simply solve for physical trajectories involving contacts and collisions using our method. For instance, here's a 2-ball trick shot on a mini golf course. We solve for an initial angle and velocity that would get both balls into the hole. And as you can see on the left, trying to do this without the Dirac delta terms produces non-physical trajectories, where balls somehow curve in violation of Newton's law of inertia. Now, here's a second, more complicated setup. Starting from an initial physically incorrect trajectory, our method accounts for banking off of the wall, continuous gravitational potentials, and making sure not to hit the windmill blades. We can find two different solutions depending on whether or not we choose to model friction or not. So these are two pretty simple examples, but they point the way to some very important different application spaces. Correctly understanding discontinuities as a language mechanism will allow us to build differentiable renderers that retain shading subsystems as programmable subcomponents and enable higher quality 3D reconstructions than current methods allow as a result. Meanwhile, correctly understanding discontinuities in physical trajectories should enable advances in optimal control and reinforcement learning for both animation and robotics. Stepping back, the key insight for this project was that so long as application programmers have to discretize their problems before programming them, they'll have to compute certain important derivatives by hand. But when we renegotiate where the language interface goes, this isn't true any longer. It does, however, open up some interesting questions about how to accelerate these discretized programs, which end up looking a lot like the array programs that we talked about earlier. And this all brings me to talking about programming the sorts of new hardware accelerators capable of giving us bleeding edge performance. Here are my collaborators on the two different projects that I'll mention in this part of the talk. So if you recall at the beginning of the talk, I mentioned the performance engineers who write, mostly by hand, the high performance library kernels for key subroutines in machine learning stacks. These high performance or HPC libraries occupy a key role in machine learning systems today. So thanks to a stovepipe system design, models built from dense and convolution layers can reliably be targeted down to hand-tuned HPC code, running on custom accelerators like Google's TPUs or Apple's Neural Engine. One consequence of this system design is that the key portability interface is defined by these library APIs and not by the hardware ISA. A second consequence is that all performance gains from accelerators are limited fundamentally by the efficiency of this library code. However, there's surprisingly little work on programming languages to help performance engineers write these libraries, which is a shame because it's a very peculiar and interesting sort of programming. So normally, if you're writing some code, you expect your code to change rapidly as a programmer, as a programmer develop software. You fix bugs, you add features, etc. Meanwhile, the hardware ISA, only changes much less frequently, and the cost of any changes to the hardware ISA is absorbed by the compiler writer who has to develop new backends. By contrast, the situation for HPC libraries is reversed. The specification of what programs should do, for example, BLAS, basic linear algebra subroutines, changes least frequently, even as hardware keeps getting updated. And even more frequently than either of those two things, performance engineers have to constantly experiment with different ways of computing the same thing in order to find new optimization opportunities. So the main approach in research to addressing this has been to try to automate this optimization process. But full automation would prevent performance engineers from doing their job, instead delegating it to compiler writers. And this is usually a losing cost-benefit proposition because even modest gains in efficiency save millions upon millions of dollars at scale. So to help performance engineers be more productive, we're proposing an approach we call exocompilation, by which I mean a language and compiler design that gives programmers more control by turning compilers inside out. Our approach to exocompilation is built on two ideas. First, the definition of new hardware backends is pushed out into user-level libraries. And second, user scheduling externalizes the responsibility for code optimization back to the performance engineers. Concretely, we designed a new language named EXO. EXO is an imperative procedural array language that's isomorphic to a subset of C. You can see a basic implementation of matrix multiplication on the slide here. And just so we're all on the same page about what performance optimization is like, here's a fully optimized version of matrix multiplication for the AVX512 instruction set, written as well in EXO. It's both orders of magnitude more complex and performant, even though it computes the exact same thing. Okay, so let's look at what it means to externalize hardware targets. As I was saying a second ago, in a traditional compiler, which includes most DSL compilers, including Halide, TVM, and the like, the cost associated with targeting a new piece of hardware ends up falling on compiler writers, and this is a consequence of the system architecture. But in EXO, this responsibility is externalized to users instead. So this kind of system decomposition is particularly valuable and necessary when hardware interfaces are proprietary, and during the development of new hardware, since the ISA is inherently unstable at this point in time. There are a number of different things that go into externalizing a hardware target in EXO, but I only have time to mention custom instructions right now. In EXO, instructions aren't special. They're just sub-procedures that happen to splice in custom strings during code generation. These strings function as a kind of macro that you'd expect with like an assembly intrinsic. So by providing both this annotation and an EXO procedure, the library writer provides the compiler with a precise semantics for the instruction, but they don't have to learn any additional new logical specification languages. They just use the language they already learned, EXO. The other major idea here is that the choice of how to optimize code should be controlled by performance engineers rather than by compiler algorithms. Specifically, we ought to be able to write this simple code and end up with this optimized code by supplying some auxiliary metaprogram that we call a schedule. This idea, which is called user schedulable languages, has grown in popularity over the last decade as a way of writing high performance code. And because the idea is still so new, EXO advances the state of the art in at least two important, if seemingly obvious ways. First, scheduling is viewed as a process of rewriting programs rather than annotating them. And second, scheduling in EXO handles procedure abstraction. So in our approach to user scheduling, both the original and optimized programs are EXO programs. So a large schedule can simply be thought of as the sequential application of program transformations, mapping from valid EXO programs to other valid EXO programs. Whenever we do such rewriting, we establish the equivalence of the procedures involved. And so given a procedure that calls one procedure, we can swap it out with a call to the other procedure instead. We can also inline the call to some sub-procedure, and in the opposite direction, we can pattern match some chunk of code against a sub-procedure and replace it with a procedure call. In the case that this sub-procedure is an instruction, we'll just have retargeted our program to the custom hardware. So we just saw 3 EXO scheduling operations that work with sub-procedures, but the full set of scheduling primitives is much larger. EXO checks the correctness of all scheduling operations using an SMT-based program analysis that I'm not going to get into the details of right now, but I'd be happy to talk to you more about later. And all of this allows performance engineers to cognitively offload the problem of correctness to the compiler writer, just as the compiler writer offloads responsibility for performance optimization back to the performance engineer. So to validate this approach, we used EXO to optimize matrix multiplication and neural net convolution on 2 different platforms. And while these are 2 very specific and simple to specify kernels, they are representative of the bulk of the work in large machine learning models deployed at scale today. Representative might be the wrong word. They are literally the bulk of the work. So with less than a week of work, we were able to match MKL matrix multiplication performance on an x86 processor with the AVX512 instruction set extension, achieving near peak machine throughput. We've also had a long-running collaboration with UC Berkeley architects to work on libraries for their RISC-V machine learning accelerator, Gemini. We replaced the Gemini subroutines with versions built using EXO and evaluated on a number of layers from ResNet 50, a standard machine learning benchmark. Our new code ran considerably faster. The results on convolution layers were similar. And as with other DSLs we've seen, EXO programs are an order of magnitude more concise than the handwritten programs. Because the Gemini hardware was and is still under development, we also got a chance to observe the effect of an ISA change in EXO compared to the existing software. EXO ended up requiring substantially fewer lines of code to incorporate a change to the ISA. And one last anecdote I want to share here is that before we were able to rewrite the libraries, the Gemini team came to the conclusion that their old code, which is what's shown in blue here, had run into an instruction issue bottleneck. As a result, they added additional hardware control logic to boost efficiency beyond what we were able to achieve in a short period of time. There's essentially hardware finite state machines that unroll some of the innermost loops of some matrix multiplication. So it might be the case that some or all of this control logic could be discarded if we had to just improve the EXO code some more, saving chip area and power consumption in the process. And regardless of whether or not we end up doing this, this kind of back and forth demonstrates the benefits of EXO and hardware software co-design scenarios, not just to the final product, but in helping figure out what really is going on with the hardware design itself. Besides our Berkeley collaboration, we're also working closely with researchers at Intel Labs, exploring the application of EXO to the VITA accelerator, which was developed, well, here always feels weird for a remote talk, but here at UW, and with the Accelerate API product team at Apple. And to put a point on this last one, this is the machine learning API for accelerating computations on the billion or so currently active iPhones and Apple computers. This work was recently accepted to PLDI 2022. And so we're in the process of getting a camera ready together and getting our code ready for a nice, proper open source software release. If you're interested in getting early access to the code or a early preprint of the paper, just let me know. I'd be happy to put you in touch with our team. So with EXO, we saw how scheduling code for high performance can be viewed as a process of user-directed rewriting. And while I didn't get into the details, reasoning about these transformations was actually pretty complicated because we had to worry about side effects and other features of imperative code. So in parallel, we started a second effort focused on a more functional approach, using a high-level language embedded in the proof assistant Coq, but with sufficient features to control lower-level scheduling decisions. In this setting, we were able to prove the correctness of different scheduling rewrites by proving lemmas, and we were able to repurpose the interactive proof system to become an interactive scheduling system instead. This resulted in the first formally verified user schedulable language. Okay, so to recap, we talked about how to handle previously unaddressed derivative phenomena by directly incorporating integrals and Dirac deltas into a language. And then we talked about how to use program rewriting to target new hardware accelerators as they're being developed. As I mentioned at the beginning of the talk, these are all parts of a broader effort to improve the way we construct high-performance visual computing systems. If we look below the level of the ISA, the twilight of Moore's law and proliferation of new accelerators has brought about renewed attention to the cost of designing hardware. I should stress here for anyone who hasn't seen this graph that the cost of designing new processors across all generations of process technology, meaning the size of the transistors, is dominated by the costs of verifying and validating the hardware and software involved. So to tackle some of these problems, I've been looking at new approaches to the design of hardware description languages. For example, we looked at using types rather than rewriting to control scheduling decisions in the design of streaming accelerators for image processing. This allowed us to generate designs that trade off between space, meaning how much chip area does an accelerator require, and time, meaning how quickly can data be processed. It also allowed us to create FPGA designs using between 1.8 to 7.9 times fewer on-chip resources. I'm also looking at some of the more fundamental questions of how programming language semantics, as we know them from software, break down when we start trying to describe hardware instead. In the middle of the stack, I've been working on a number of projects related to tensor languages. Most of these hinge off of a DSL I've been playing around with over the last couple of years, named ATL, in homage to Ken Iverson's APL. For example, ATL is that user schedulable functional language that I mentioned us embedding into Coq a minute ago. And it also has deep algebraic connections to the discontinuous derivative work that I talked about earlier. Two ongoing projects that I didn't have time to mention are focused on generalizing the highly efficient automatic differentiation from OPT and on optimizing neural networks with highly structured sparsity patterns arising from quantum chemistry calculations. Back on the application side of things, I've gotten pretty interested in the way we construct fabrics, garments, and other sorts of soft objects, which I'm sure seems completely unrelated. Well, maybe for most people, maybe not here at UW. Regardless, let me try and persuade you that it is quite related. For instance, in a SIGGRAPH paper last year, we developed a mathematical theory for determining whether or not a quilting pattern can be constructed with a popular and beginner-friendly sewing technique. This theory is rooted in state transition systems, like we're all familiar with from automata theory. Constructability, then, is simply a question of reachability in an appropriate state transition system. And of course, state transition systems are also the basis for much of programming language theory. If you do quilting yourself, you can try out our design tool online. I also have an ongoing collaboration with researchers at CMU who have a knitting compiler stack. We're looking at ways to verify and optimize their knitting machine programs by again recasting optimization as a form of rewriting. The catch in this setting is that the equivalences that we want those rewrites to respect are fundamentally topological, arising from knot theory, rather than simply about functions, as you'd expect with normal programs. More broadly, many of the most impactful changes to design and manufacturing will likely have to do with the interfaces mediating between designers and manufacturers. So as I close out the talk, I want to leave you with some thoughts on two of the big challenges that I've mentioned. The first big challenge I want to highlight is how we're going to program new hardware accelerators. Obviously, I have my own horse in this race, but regardless of whether or not you agree with me, the gap between naive CPU code performance and the bleeding edge of hardware acceleration is only set to widen in the coming decade. The second big challenge is how to quickly develop high-performance solvers for optimization-based applications, which I mean very broadly to include machine learning, statistics, and so on. Systems like Opt, TensorFlow, and PyTorch are at best only partial answers to this challenge, because they have huge 100 times or worse performance cliffs if your problem doesn't quite lie in the correct vertical application domain. So one thing we can do is we can keep creating more vertical DSLs for new application domains, or we can try to generalize some of the lessons that we've learned. Either way, there's a lot of room for improvement. So over the course of this talk, we looked at ways to make simulations performance and parallel portable using ideas from databases, and how to quickly generate high-performance GPU solvers using automatic differentiation. We introduced the first automatic differentiation system that handles discontinuities, and the concept of exocompilation as a way to program all the new machine learning accelerators. In all of these cases, programming languages served as a way to renegotiate the division of responsibilities between different kinds of experts. Once everyone can more easily bring their own expertise to bear, then together we can create the next generation of high-performance visual computing systems. I'll take any questions you all have.
Thank you so much for the great talk. I think there are a couple of questions from the audience. So,
thanks for the great talk, Gilbert. One thing I'm really curious about with being able to program new hardware accelerators is the change in numerics. So a lot of new accelerators play games with either custom number systems or some kind of quantization. And this is a real cross-cutting concern, right? Through all those layers, through the kernels and everything else, it affects the scheduling, affects the memory hierarchy. And I'm just curious if you've thought about how to abstract over that or make that schedulable in any way in sort of the EXO compilation approach.
Yeah, so in EXO, the way we deal with this is we just say, it's all equivalent from the point of view of equivalence of programs, and then you can go in and adjust it as you want. That doesn't necessarily give you a good policy for how to do it. So I think that's something which would make sense to add in secondarily, because definitely you don't want to go through every single point in the program and annotate it by hand. That's a little maddening. One of the things I didn't talk about so much with EXO is we're trying to get sort of the core of it, but one of the next steps we're doing is offering a way to compose together the scheduling operations to build sort of higher levels and more semi-automated scheduling on top of it. So you could imagine having some sort of method that crawls over the program and starts making some of those decisions according to some policy, but that's all externalized from the compiler as well.
Yeah, I could almost imagine, well, we should probably continue offline, but like, one of the things you did, I think, at every stage of the talk was imagine that floats are reals, or that, everything's a field. Yep. It just works. And like,
that's the way to do it.
Oh, it's great for equivalence. It's great for search and optimization, all these things. And I wonder if some of these layers you're talking about, you almost want the compiler maybe to move through phases where your notion of equivalence can become finer grained depending on what the hardware requires of you, pulls out of you. But yeah, super exciting stuff. Really, really excited to keep chatting about it.
Yeah, in the work on just really declaratively expressing derivatives along with the behavior at discontinuities, what about when the expert doesn't know where the discontinuities are, or is that just something that those experts just do for breakfast and I don't?
There's different degrees of I don't know where the discontinuities are. What this allows is essentially parametric discontinuities, and arguably you can build those up into all sorts of other discontinuities you'd be interested in. So if you think about like, okay, I'm not sure at what time or position along a wall that ball in the mini golf example is going to hit the wall and ricochet off of it, that's all left free. You can say in different ways there, like, so you could say, I'm going to say topologically, like the ball's going to travel some amount of time, hit one wall, hit another wall, and then go in. I could bake that into my model. It's also possible that I can just have my trajectory allow for at regular points, if it's some sort of spline, if that makes sense to hopefully some people, you could allow for some of those knot points or particular points along the spline to be either discontinuous or continuous. And you could have an energy which would prefer them to be continuous, but would allow under suitable conditions, like, there's a wall, for that to break apart.
Yeah, it's really that last part I think I was most sort of interested in, which is, well, yeah, I want this integral. I expect there to be ricochets, transformations, whatever it might be in my particular domain. And, maybe I even know there will be two of them, but I don't necessarily want to specify the algebra about where they are because I might be wrong, or it might be beyond my understanding analytically.
Yeah, I mean, you could view it as similar to some dynamic programming problems. Like, I don't know if this will make sense to people or not. The line breaking algorithm in tech is actually inserts essentially a bunch of variables between each token and says, do I break a line here or not? And then it solves for those. You can imagine along your trajectory, you have some number of variables which are, am I continuous here or not? Or that's implicit in the way that it's encoded. And so you can have potentially many opportunities for those discontinuities that aren't realized.
You mentioned in a slide that when ISA changes, you only change several lines to adapt to that change. So I wonder what level of ISA change you are mentioning to?
I think that one in particular might have been some change to some configuration instructions. But sometimes it's really trivial stuff, like you're just rearranging whether or not a parameter is set and stored in processor state versus passed along with instructions. It could be adding if it's adding a whole nother instruction, obviously you're gonna have to write a new instruction if you want to take advantage of it. But that kind of stuff. I mean, if you're completely changing your model of what you're doing with the processor, then yeah, obviously you're gonna have to rewrite things. But
so that's basically some parameters that, for example, changes the bit of vectorize as something like that. Is that right?
Yeah, as well, like if you add features, like I'm trying to think of other features. So there's a lot of features on Gemini that allow you to do like striding of memory accesses. Or maybe you added a new kind of activation function. And so now you have a different enumeration bit. Now you need 2 bits instead of 1 in that instruction. And it's a small, silly thing, but accommodating those changes rapidly and in a way that, in fact, the hardware designers can go in and modify that rather than having to toss it over the wall to a compiler expert is pretty useful.
Thank you.
Kind of follow up on what Dan was asking. So the way that you can handle the discontinuities is because the problems that you're dealing with, right? Usually you're integrating over them, right? I would love to understand, like, is this, and of course in graphics that happens a lot. Do you think this can be extended in ways where you don't have integrals, or like what are the limitations, or how can you expand this to other sets of problems?
Yeah, so it is very important that they're being integrated over, because it means that the overall derivative is already well defined. So what we're not doing with this work is trying to just by fiat say, here's what derivatives of discontinuities mean. There's a correct answer to the problem we're solving by virtue of that. If you get into the territory where it really isn't well defined, then you end up playing various tricks where you modify the problem to get an answer. That said, one of the interesting things that's like very much a programming language's point is that the fact that something is being integrated and the specification of some subcomponent of the model that's being integrated are most often you want those to sit in 2 different files. So a great example would be a shader. It's not the case that the overall process of rendering those integrals lives in the shader, and yet it has to be inserted into that context. And by virtue of that, then you have to start dealing with these problems.
That makes sense. Yeah. So this, great. Yeah. Thank you so much. And I guess Gilbert will be around to chat with more folks later on. Yeah. Thanks for the wonderful talk.